I'd like to talk for a minute about a experiment I did, a greenhouse gas experiment. I call it the re-radiation greenhouse gas experiment. I had really two hypotheses I was looking at here. One of them is that water vapor generated by the combustion of hydrocarbons and other human activities contributes more to the greenhouse gas effect than carbon dioxide. For example, the combustion of methane, which is really a pretty green fossil fuel, you got a pretty high hydrogen to carbon ratio compared to most fossil fuels. You end up with carbon dioxide and water vapor when it combusts completely. But you also got a lot of other human activities such as watering yards, agricultural irrigation, washing cars, just breathing, increasing evaporation from rivers, streams, lakes, dams, etc. So a lot of ways humans are putting more water vapor in the air. And I believe in the greenhouse gas effect. We'd be freezing at night if it wasn't for it. So I just wanted to try some experiments, and that's what I'm talking about here. Now, NOAA's got a couple websites, not only show an increase in carbon dioxide, but also an increase in specific humidity since 1971. If you go to, there's a number of references you can look at here. Very good information. You can see that if you look at the spectral output of the sun in wavelength ranges and where water vapor and carbon dioxide absorb at, it's pretty clear water vapor's got a much broader ability to absorb infrared probably than carbon dioxide. But back to this experiment, I made an adiabatic, which just means insulated test chamber, designed to minimize the heat conduction into or out of it. I made the inside reflective with Reflectix insulation, so the only path for the IR or heat is through an insulated glass window at the top. I had trouble finding a standard non-low E insulated glass window because that's about all they make anymore is low E, which is good for your house, but not good for what I was trying to do here. I put a flat black painted surface at the bottom to absorb light from a heat lamp and have it re-radiate back out through the window. Then my intent was to monitor the rates of temperature increase and decrease over time, compare the results for dry air, humid air, dry carbon dioxide purged into the test chamber. This is what my apparatus looked like, a schematic of it. This is just a trash can, insulated with great stuff. That's what this kind of a beige color is on the outside. The inside was covered with Reflectix, which is very reflective and also insulating itself. The top was a homemade insulated glass window made with two 1/16 inch standard window glass panes and a 250 watt Phillips heat lamp. A couple of gas purge ports, one here, one down here. I used just a steel baking pan turned upside down, painted flat black. And on the bottom of that, I attached, just with a bolt, screw and a nut actually, a thermocouples, type K thermocouples, and two of them coming up to a dual input digital thermometer. Here's the other one up here. And then used this was an Omega, and it worked really pretty well. I had a USB cable connected to a laptop, was able to use their software for data analysis, and I just copied all the data and put it into Excel, and I got a lot of data. But the idea was that this heat lamp would shine down through whatever gas was in here, and it may or may not be absorbed by the gas on the way down, and then hit this flat black surface. This would heat up, then turn off the heat and let this heat re-radiate back out through here, and then measure those differences in temperature over time and see what it looks like. Quickly, my results were I measured no difference between in rate of temperature change for dry air, humid air, or dry carbon dioxide. So I'm going to show you my data. Okay, this is charts for the data. I actually did each set of experiments 4 times, repeated it 4 times to make sure I had enough data in case I tripped over a wire or something. So I'm pretty confident this data is accurate. Did a good job of purging the test chambers, but Interestingly, what I did here is I started out at about room temperature and just simply turned on the heat lamp. You can see the heat rise. At about 150 degrees on each experiment, I simply unplugged the heat lamp and it started cooling off. Followed this profile. And I used dry air, CO2, and humid air. And I'll show you some actual videos of the experiment, how I got the CO2 and the humid air in there. But these curves fall right on top of each other. This is all T1 data, which is that connection down to that flat black surface. Over here is the T2 data. It didn't heat up as much. But basically, a little bit of anomaly there on the carbon dioxide data. Not sure why, but pretty much follows the same slope. So this is something I did not expect at all. So really my conclusion was based on the spectral output of the Philips infrared heat lamp and the absorption spectra for water vapor and carbon dioxide, that it's quite possible I simply missed where these two entities absorb infrared at. Because if you look at 150 degrees F and calculate the black body radiation of that, I mean, you're looking at something like 7.7, I believe, microns, and carbon dioxide absorbs at about 4.25 and about 15, and two significant peaks. You know, that's right in between there. So my thinking is I just simply missed the ability for carbon dioxide to absorb the infrared that I was subjecting it to. So my next experiment will be to use sunlight as a radiant source, and then to measure a difference in maximum temperature in direct sunlight, and also be re-radiated sunlight from a black surface at normal Earth re-radiation temperatures. 150 F is a little hot. So that's my next experiment. So again, these were my references. They're worth looking at, good information. I'm not in any way affiliated with any of this. And so what we'll do now is I'll show you a few videos of the actual experimental setup, and then we'll go on to the next attempt to demonstrate this. Thank you. You know, I've had some bad ideas in my time, but using great stuff to insulate this trash can for my greenhouse gas experiment, that ranks right up there with the worst of them, that is for sure. What a mess. I had no idea it was going to sag like this. Maybe it's salvageable, we'll see. This is an ordinary, inexpensive steel baking pan. I put a stainless steel screw in the bottom of it to attach the thermocouple to. And when you flip it over inside the test chamber with the spacers on it, and then I painted it with a flat black paint as a heat-absorbing, re-radiating surface, and this seemed to work pretty well. Okay, inside, what we got is the inside of this trash can is lined with Reflectix insulation, again, just in building supply, some weather stripping on top here to form a gas-tight seal. Underneath this right here, I've got a little piece of plastic tubing. My top thermocouple comes in right. This is my new re-radiation greenhouse gas experiment apparatus location and setup. Computer here, software on it, my dual input digital thermometer, my test chamber is thoroughly insulated with insulated glass on top. Down at the bottom, it's a little hard to see from here, there's a port I've got at the bottom where I can introduce gases, and then another port here where I can go either way with the gas depending on what I'm trying to do. And what I use this for is light that candle, and then if I'm purging carbon dioxide, when it finally comes up, it comes out here, it puts the candle out. That works real well. We'll give this one a try. Got a 250 watt heat lamp bulb in here, and we'll see how this one works out. This is how I'm purging air through my silica gel desiccant. I got it sealed up, connected with air on one end, wrapped tight, so the only way the air can get through it is through the silica gel that's going into the bottom of the test chamber. Over here, you can't see it, but I can feel the air coming out. So we'll let that purge for about 10 minutes or so. If you listen closely, you can hear the sound of my carbon dioxide purging into the bottom of the test chamber. Well, what it'll do when it's filled up with CO2, we'll see that candle burn out. Okay, it went out. Let's see if this will hold a flame. Now we'll put a rubber stopper into this. Okay, I used a wet sponge to purge the chamber with humidified air, and that worked pretty well. That's what this yellow sponge is for. Just put a little compressed air through it so to pick up moisture. Okay, this is what the experiment looks like when it's running. You can see the black re-radiator surface down at the bottom of the test chamber. And right over here, you can see it right underneath there is a top thermocouple. That's the T2 thermocouple. The T1 is down at the bottom. It's attached up underneath that pan. Okay, you can see, it's a little hard to see here. This bottom line's the one that's at the top, the T2. The top one is the T1 line. And I can record this data with this software for the Omega, and then just copy those files. And right now I'm getting a data point every second. I can copy the files, put them into Excel. You can see here, if you look closely, you'll see the top larger number is the T1. You can see it closely. The bottom one over here on the left is T2. This is the time. So that's basically how the apparatus works. And so we'll review the data.